Hello everyone. My name is Li Lin from Purdue University. Today, I'm excited to present our work titled AI Face, a million-scale demographically annotated AI-generated face dataset and fairness benchmark. Let's begin by looking at some examples of deepfakes. On the screen, you see 3 high-profile cases, fake images or videos of Donald Trump being arrested. AI-generated faces, like deepfakes and GAN or diffusion-generated images, are increasingly realistic and widespread. While these technologies can enhance creativity and entertainment, they also pose serious risks. One of the most critical threats is the spread of misinformation, which can influence public opinion, manipulate narratives. However, face detectors often misclassify these images, especially unfairly across demographic groups. For example, the misclassification rate of real faces as fake can be over 26% for some groups, while only 8% for others. We need fair detectors to prevent deepfake misclassifications that can manipulate public opinion and undermine trust in detection systems. Yet, developing fair detectors is difficult because existing datasets either lack demographic labels or diversity in generation methods. Then how can we evaluate the fairness of current detectors and develop fair detectors? First, we built AI Face, the first million-scale dataset of AI-generated face images with demographic annotations, using our own fairness-aware annotator. Second, we created the first comprehensive fairness benchmark, evaluating how well 12 representative detectors perform across different demographic groups. And finally, based on these experiments, we identified several unsolved challenges and offered key insights that can help guide future research in building fairer and more robust face detectors. Here's an overview of the AI Face dataset. Unlike prior datasets that only cover deepfakes or offer limited demographic info, AI Face includes 3 types of generated faces: deepfake videos, generative adversarial networks, and diffusion models, and provides annotations for gender, age, and skin tone. We collected over 1.2 million fake and 400,000 real images from 28 public datasets and generation models, covering 37 generation methods in total. Here is our dataset generation pipeline. For skin tone, we estimate it using the Monk skin tone scale with k-means clustering over facial skin regions. For gender and age, we build a clip-based model, trained on IMDb Wiki, and optimized with imbalance and fairness loss, along with sharpness-aware minimization to improve generalization. This design helps mitigate the inherent biases of clip and the label imbalance problem, producing more reliable annotations. With this dataset, we benchmarked 12 AI face detectors from 4 categories: naive, frequency-based, spatial, and fairness-enhanced. This table shows their average fairness and utility metrics. We found that fairness-enhanced models like PGFDD perform best overall, showing high utility and low bias. Also, University FD, which uses a clip backbone, achieves good fairness, suggesting that foundation models, when enhanced, are promising for fair detection. When we analyze fairness across different image subsets, we see that the largest bias arises when detecting diffusion model-generated images. Even fairness-enhanced models struggle here. However, models like DAGFDD and SRM show more stable fairness across subsets, indicating their robust handling of bias introduced by different generative methods. Next, we evaluate robustness. We apply 6 common post-processing methods like rotation, brightness change, and compression. These often degrade utility, but interestingly, some methods improve fairness slightly. For example, UCF, University FD, Core, DAW-FDD have better fairness after rotation. Unfortunately, even fairness-enhanced detectors struggle to maintain fairness under post-processing, highlighting a limitation in real-world deployment scenarios. From our findings, we draw 3 key conclusions. First, fairness is unstable across generation methods, especially newer ones like diffusion models. Second, even the best detectors still show bias toward minority groups. Third, no current detector is reliable under post-processing or domain shifts. Therefore, future work must aim for detectors that jointly ensure fairness, robustness, and generalization. Thank you for watching. Our dataset and benchmark are available on GitHub, and the paper includes further details.